Welcome back to our online classes, and in today's lecture we are going to study chemical thermodynamics. And in thermodynamics we study the relationship between heat, work, temperature and energy within the universe. Thermodynamics comes from two words, thermo, which means heat, and dynamics to means something in motion. So it means when something is in motion, and let's take an example of matter. Matter can be in terms of gases, liquids or solids. So let's take an example of a particle of, let's say, argon gas. At a certain point, the particle of this argon gas can be at point A, and then at point A it will possess a certain amount of energy, and it can also change its position to, let's say, point B, and in point B it will also possesses a certain amount of energy. Now, during this transition or change in position, it was also possessing a certain amount of energy for it to change from point A to point B. Now, when you look at exact position of this particle, that position itself is what we refer to as microscopic properties. So microscopic thermodynamic properties are properties of particles within the universe due to their either positions and even the velocity, because when this particle was changing its position from A to B, it was moving at a certain velocity, while now at point B or at point A, or during the course of this transition, there was energy which was being possessed. This energy at point A and at point B is due to their position, while between point A and point B it was due to the motion. So this energy is an example of what we call microscopic property. Macroscopic properties are bulk properties that we can study and measure and describe how they behave, while microscopic properties are properties at a lower level, and this can be due to their position. So the interaction of microscopic properties and macroscopic properties within a universe is what we call thermodynamics. The study that involves between these particles' position and the energy it possesses is what we call thermodynamics, the study that involves. Within thermodynamics, then, we can have some terms that we can define, like energy, which is the ability to do work, and that's what we call energy, and energy is measured in terms of joules. We also have temperature, which is the measure of coolness or hotness of an object. For example, you can touch a stove or a cooking pot, right? It is on the stove, you touch it and then you feel hot. And if you touch an ice, you feel cold. So that measure of either coldness or hotness of an object is what we refer to temperature. Then we have work. In physics, we define work as F(d) cos theta. That is the force applied at a certain displacement due to a certain angle made with the ground, and we define it as Fd cos theta, and this theta will vary. Now we are saying for you to do work, there must be a change in position. So if there's no change in position, even no matter how much amount of energy that you put in, there won't be work done. You can't be pushing a wall the entire day, you are using a lot of energy, but the wall does not move, then there's no work done. But if I take a pen from the table and then put it on the chair, I've done work, because there's change in displacement from point x1 to point x2. So work is the transfer of energy due to a change in position. When we talk of it, we are transferring energy due to temperature difference. So then we can put energy into ice at 0 degrees Celsius, and we increase the energy, we put more energy, and then it increases until it reaches, let's say, 25 degrees, and then it means that we are putting heat to that particle. Sometimes, for example, if you are feeling cold, you can rub your hands, and transfer of energy due to temperature difference is what we refer to as heat. Now, We have talked of energy as the ability to do work, and this energy can be in terms of kinetic energy, which is the energy due to motion. For example, if I am walking or running, meaning that the energy is due to the motion that I am applying, and that is kinetic energy. Kinetic energy is then given by a half of the mass of that object times the square of its velocity. At a certain point, for example, if a car is moving, it is in motion, and the energy it is possessing during that motion, it is possessing what is called kinetic energy. We can also have potential energy, which is the energy of an object due to its position. For example, you can put, if there is our stool, okay, or our table, and then you put an object here on top, so this object is at rest, it is not moving at all. So the energy it is possessing at this point is what we call potential energy. And you can see, if this is the ground, there's a certain height it has, so this can be our height, and this object possesses a certain mass, so it has a mass within it, and because it is on the surface, then there's gravitational force of gravity which is acting on it, and that is G. And then we can say potential energy of an object is given by its mass times gravitational force of gravity, or pull of gravity, times its height. Now let's take an example of a molecule. Let's say we have a molecule, let's say like CO2. So CO2, so let's say CO2, right? Now this molecule at a certain position, or at its position, it possesses potential energy. And now if you supply heat to this CO2, when it absorb it, or let's say now you are decomposing it, meaning that it is going to absorb it, then this bond will start to vibrate, and then they will even dissociate and even break up to give you other particles. During that moment, when now the bonds are now starting to vibrate, it means that you are converting potential energy into kinetic energy. So it means that within the universe, for example, if this was a reaction, then in that reaction we'll refer to it as the system. For example, this container where the reaction is taking place at a system, we'll look at a system, what is system, and surrounding at later stage. But now let's say during this reaction in this vessel, we have potential energy of this CO2 and its own kinetic energy. We can then ask ourselves then, what is internal energy? Internal energy of the system, of this system, then will be the sum of, so we can say internal energy will be the sum of all the potential energy of this particle plus all the sum plus all kinetic energy of this molecule. During a reaction, there are processes that can take place. If this is our vessel and the reaction is taking place inside, then energy of these particles can be lost, in the sense that they can move out of this container and go outside the container. So if this is our point B and this is our point A, okay, so the energy can be lost during chemical reaction from point A to point B. And our point A is the point of interest, and we'll study and define what it means when we say it's the point of interest. So when energy is going out of the system to outside the system, which is the surrounding, so this is the surrounding and this is the system. So when energy is moving from the system to the surrounding, we say that is a process called exergonic process, because the energy is released by the system to the surrounding. So it therefore means that the energy of the system will drop while the energy of the surrounding will go up until it reaches at a point of thermal equilibrium. When we talk of endogonic process, is a process now, instead of the system losing or releasing energy to the surrounding, the system now is absorbing that energy. Now This is the surrounding and this is the system. So now the energy is flowing from the surrounding to the system. It means that the energy of the surrounding is decreasing while the energy of the system is now going up. So when the energy is being absorbed in the system, meaning that it is being released by the surrounding, then that process is called endogenic process. We also have what is called exothermic process, and thermic comes from word thermo, which means heat, because it is exo, meaning that the heat is being released. So again, in our reaction A and B, sometimes the heat can be released from point A to point B, meaning that from the system to the surrounding, and that is called exothermic process. It means that heat in the system will go down while heat in the surrounding will go up until it reaches a point of thermal equilibrium. And when this happens, you can feel that the reaction vessel or this container is at least warm because the heat is being released. So how will you feel it is warm? Because when you touch it, you will absorb that energy, that heat. When we talk of endothermic, thermic still means heat, and endo here means inside, and this is our system, which is A, and B here is the surrounding. So now, instead in exothermic, we saw the heat was moving from system to the surrounding. In this time round, the heat is moving from the surrounding to the system. So now, when the heat is moving from the surrounding to the system, the heat in the surrounding will decrease, while heat in the system will increase until the two reaches at a point of equilibrium. Now, during all this process, you realize that there's what separates this system, point A and point B. So there's this boundary in between. It is this wall that is going to explain and show the interaction and the relationship between the system and the surrounding. Next, we can then look at the system and the surrounding. We have the universe. The universe entails, we have the universe, which is everything. So this universe entails the system, and it's also entails the surrounding. Okay. So now, what is the system? System is the specific area of interest or the area of the study. If the reaction is taking place inside this container, then this container, inside this container, is what we call the system, because it's the area of our interest. Now everything outside this system, meaning outside here, this is the surrounding. But you realize that all of them are found within the universe. If we check in, there's a wall separating this system, so system and surrounding. So if we check that between the system and the surrounding, there's a wall. Okay, there's a wall in between. As we said, that we can call it a wall or a boundary, and this boundary can be physical or it can be conceptual. It's something that you can think exists, and we are going to see practical aspects of this boundary. And as we have said, that it is this boundary or this wall that is going to show the relationship between the system and the surrounding. This wall is very important because it can be selective or non-selective. So the way the system behaves is the way the system and the surrounding interact with each other is being determined by the nature of this wall that separates the two. And it is this wall that is going to determine the types of the system that we have. Now, when you look at the types of the system, then we can have an open system. An open system is a system that can allow the exchange of matter and energy with the surrounding. So for example, if this is the system, and this is the surrounding, it means that open system can allow the exchange of matter and heat to go between the system and the surrounding. Okay, and the surrounding. A good example of an open system is when you are cooking. You are at home cooking, and this is the heat from the stove, and this is the water that you are boiling. Okay, so you can see this is the wall or the boundary between the system and the surrounding. So because this our pot is not covered, it is open, so you find that in the surrounding this heat, you heat this pot, it absorbs it. It means that it exchanges it from the stove to the inside the pot, and then the water absorbs this heat, the water boils, and then the water vaporizes into the surrounding. Okay, it vaporizes into the surrounding. And also here, heat in form of steam can be lost from this pot to the surrounding. So that's how open system behaves. It means that it can allow the exchange of matter in the system and also into the surrounding. So both of them can move in and out. If this one is physical, but the wall in between here is conceptual, is something that you cannot see. So with the open system, it has a wall which is permeable. A permeable wall means that it allows exchange of matter. Gases are escaping from this pot to the surrounding outside the pot. So it means that the conceptual boundary or wall in between here can allow water to escape from this pot to the surrounding. The wall in open system is also diathermal, meaning that it allows exchange of heat between the system and the surrounding. If it is a physical wall, then it can allow heat to come from the stove into the system and boils this water. And also this conceptual boundary or wall, when the water is boiled, it will then can escape in forms of steam, and then you can put your hand here and feel like, wow, it's so hot, you know. So the function of the thermal wall helps us to facilitate heat transfer between the system and the surrounding. Let's look at closed system. With a closed system, allows only exchange of energy but not matter with the surrounding. So if this is the system, and the surrounding, for example, let's take in case of a bulb. Okay, let's take in case of a bulb. So in this bulb there's filament, and this can be, let's say, argon gas in our bulb, and then so this is the bulb and it's closed. So the entire bulb is closed, and whatever is inside this bulb is the system. So this is the system. This glass of this bulb is the wall, and it is closed such that whatever is inside cannot come out in that case. But with a closed system, you realize that it will allow only heat or energy to move between the system and the surrounding. So if this is the surrounding outside the bulb, that is why you can put your hand closer to this bulb and feel that you are warm, because this allow heat to come through. It allow heat to come through out of the system to the surrounding and surrounding to the system, but matter cannot come through because it is closed. Okay, this argon is closed here, so it cannot move. So that makes the wall of this closed system to be impermeable. Number one, the wall can be impermeable, meaning that does not allow the exchange of matter. Diathermal, this wall, however, it is diathermal because it's allowed the exchange of heat between the surrounding and the system. That is why if you place your hands closer to this bulb, you will feel that it is hot. Now, what's the function of this diathermal wall? It facilitates the heat transfer between the system and its surrounding. So in that case, then we can proceed to the next type of the system, which is the isolated system. With the isolated system, it doesn't exchange any matter or energy within the surrounding. A good example of isolated system is, for example, a thermoflask. So this is a thermoflask. Okay, this is a thermoflask, the one that we use to keep tea. All right, so it is closed. All right, you have tightened up here, and you boil water. Or you have prepared your tea until it is inside, it is full. So now the heat this is in the morning, let's say 7 a.m. in the morning, and you come back at, let's say, 2 p.m., the tea is still hot. So it means that there was no change, there was no exchange between the surrounding and the system inside this flask, because it was totally sealed. And if you look at that thermoflask, there's an insulator, there's a material which is insulator, and this one cannot allow the exchange of heat or matter between the system and the surrounding. Now, you realize that when you come back at, let's say, at 4 and you want to take your tea, it is still hot. It means that it is hot because there was no heat which was lost. And with the isolated system, most of them are insulators. However, there's no perfect isolated system, because at a certain point, for example, if you leave this tea in this flask for 1 week or 2, it will cool, meaning that the temperature will go down, meaning that it will have started to lose heat. So we say that there's no perfect isolated system because there's always an interaction between the system and the surrounding. Now, the wall of the isolated system is impermeable, meaning that it does not allow the exchange of matter. Matter here can be in terms of gas, solid, or liquid, but majorly will refer to gas. The walls also are adiabatic. Adiabatic means that it does not allow the exchange of heat between the system and the surrounding. So the function of adiabatic wall is that it prevents heat from flowing in or out of the system. So in another word, it helps to maintain the heat of the system and the surrounding. So in a summary of the system, we can then say that we can have the system. This system can be open, it can be closed, and it can be isolated. Now, when it is open, it means that it can be permeable and it can be dithermal. So permeable means that it allows matter. Dithermal means that it allows heat or energy. When it is closed, it means that it is impermeable. Impermeable meaning that here if we have matter cannot go out and in. However, it is dithermal. So it means in terms of heat, it's okay. It can exchange heat within the system and the surrounding. But isolated, we can have it is impermeable also. Impermeable meaning matter cannot pass through, and it is also adiabatic. Adiabatic means that heat cannot go through. So this is the first part of introduction to chemical thermodynamics, the type of the system that we have, and how the system interacts with the surrounding. The most important thing to note is that the system is the area of interest and the surrounding is anything outside the system. That marks the end of our today's class. Thank you for watching. If you have not subscribed, subscribe to our YouTube channel for more updates and uploads. Thank you for watching. See you in the next class.